Good afternoon, ladies and gentlemen. Welcome to the presentation on GPS EGNOS performance for rotorcraft operations. With the increased use of satellite-based navigation in aviation, also the possibilities for rotorcraft operations under instrument flight rules are significantly enhanced. One of the examples is the Swiss low-flight network, and it's a low-level route en route network and pointed space approaches to helipads as well as hospitals. The green lines, by the way, are the routes already implemented. The purple lines are still the plans where we have to work on. However, you certainly heard of GNSS deficiencies. GNSS signals can be shaded due to terrain. You heard probably of jamming events where GNSS was not available at all. And the focus of this project, the heli recording random flight, was to assess the performance of GPS EGNOS for aviation purposes in the Swiss airspace. We didn't want to have just a few dedicated flights, but we really want to have a statistically relevant data sample where we can see what the performance is for all the flight levels and the whole Swiss airspace. Rega, as well as the Swiss Air Force, was in favor of this project, and they contributed with helicopters, 18 helicopters of the type EC-635 in case of the Swiss Air Force, 6 helicopters EC-145, and 11 Augusta-Westland 109 SP helicopters in case of Rega. All these helicopters has been equipped with a dedicated mini quick access recorder, which was recording data directly from the GPS receiver, FMS, as well as AHARS. From GPS receiver, we got position, altitude, time, protection level, and for the EC helicopters, we did also have access to range information, which allowed more enhanced analysis. For evaluation purposes, we also recorded flight management system data, position, altitude, time, speed, and when available, when the pilot was doing a dedicated procedure, when flight plan data was available, we also recorded this information, as well as data from the attitude heading and reference system, pitch roll, and heading. The project duration was 5 years, and during these 5 years, we recorded a bit more than 40,000 flight hours. Flight hours have been recorded, the flight data has been recorded in whole Switzerland. You can see here the samples, the measurement samples per kilometer square. Mention we are now at flight level 0 to 500 meters above mean sea level. The terrain at Switzerland is, I would say, at least at 400 meters. That's why you don't see that much so far on this chart. If you go up 500 meters, we have much more samples, we have much more flights. Still, the flights are mainly in the northern part, in the flat part of Switzerland. The southern part are the Alps, where we are still far below terrain. We go up another 500 meters. Situation is more or less the same, but if you now go up again to 2,500 meters, you can see that the flights over the flat terrain are decreasing. The flights over the Alps are, of course, increasing up to roughly 4,000 meters, and then we don't have anymore a lot of helicopter operations, especially at 5,000 meters above mean sea level. This chart shows the overall distribution on all flight levels. We have quite a good distribution in the whole Swiss airspace, mainly in the flat part and in the valleys of the Alps. We didn't, what I showed you are the recordings from the avionics. We didn't only want to have avionics recordings, but we also wanted to have independent measurements. With that, we defined a system to get independent trajectory determination based on a geodetic GPS GLONASS receiver with a GNSS antenna with a vacuum cap, which can be mounted up on the helicopter windows here, GPS receiver inside the helicopters. And with that, we are able to determine the real trajectory of the helicopter with a decimeter level accuracy. If the helicopter is flying at procedures, we can derive the total system error here with, as said, decimeter level accuracy. Just a short recap here on the error, on the different errors. What I just showed you was the true flight path, which is derived with this independent system. The desired flight path would be the flight path on the chart, and what we record with our avionics system would give us the navigation system flight path. The difference between navigation system flight path and the desired flight path is the flight technical error, which is mainly the quality of the autopilot, or let's say the quality of the pilot. Also wind components are covered here. The total system error is everything, and the difference here, of course, is the navigation system error. We are working in the 0.3 environment. According ICAO PBN concept, 0.3 environment means the total system error should be less than 0.3 nautical miles during 95% of the flight time, and the flight technical error less than 0.25 nautical miles during 95% of the flight time. One of the analyses we did in the frame of this project was an extensive trajectory analysis with more than 100 flights, mainly north-south, but a few flights also on the east-west segment of the low-flight network. Pilots were making notes on the waypoints. They joined the network, and on the waypoints they left the network, and they also noted all abnormal behavior during the flight. That allows us to have a good data set which is able to really assess the quality of this network and of the GPS EGNOS performance. Here's an example, the left chart with 4 flights over the Alps from the north to the south. You can see different flights are joining here and flying the low-flight network, the route from the north to the south. The right chart is showing you the deviation from the design track to the navigation system flight path, or in other words, the flight technical error, which is far below 0.1 nautical miles. What you imagine when you have a first look on the chart, the largest peaks are close to the waypoints. The reason for that is in an en route network, we only can design straight segments. If we have 2 straight segments, one following the next one with a significant track change, then the autopilot or the avionics system is apparently doing an anticipation of the turn and is not going over the waypoint, but is flying a flyby waypoint, and that gives in the chart on the right these false peaks, which are not errors, but which are normal system behavior. Apart from this, you hardly can see any deviation from the desired flight path. To be a bit more statistical, I made a histogram of the flight technical errors of 21 hours of flight time recorded under this RMP03 performance. You can see the mean is quite at 0. The 95th percentile of the flight technical error is roughly at 0.015 nautical miles. I just put the PBN manual requirements down here as a comparison, which is 0.25 nautical miles for the flight technical error. So in summary here, we exceed the requirements of the PBN manual with a very, very large margin. What we did also in this project is to see how far we could go. This is a dedicated route which starts with an ICAO-compliant part up to the waypoint 105 here. Afterwards, the routing is getting more and more difficult, far below what ICAO allows, and also far below what the helicopter manufacturer, in this case an AW109 SP, specifies what he can fly. We have here a 360, we have here an extremely narrow S-shape, and at the very end, a holding with an RF holding. That's how the helicopter performed. Of course, the ICAO-compliant part was made without any significant deviation. If you go up a bit more, even the 360 here you can see the zoom, was made extremely accurate. Again, as I already said, again, this is far below what helicopter manufacturer states what the helicopter can do, and far below ICAO requirements. The narrow S shape here, you can see the first issues. The helicopter needed additional track miles to get on the track again, and also for the RF holding, there are some deviations visible. With this kind of procedures, we are able to assess what can be technically done and where we have the limits. So it can be clearly seen here that it could technically be more than what currently is possible with the ICAO criteria. If you have a look at procedure design, the Swiss Low Flight Network is an en route network based on RMP 03 specification. If we design such a route, then we have to design a primary, secondary protection area, which goes 1.45 nautical miles left and right of the desired track. If we are in a valley, in Switzerland we usually don't have that large values. So if you have to design the whole procedure with this protection area, we have to go up with the flight level, usually more or less at the top of the mountains. Here you of course have icing issues, which is not what we want, and the intention would be of course to go much lower with our networks. An example here is the RMP 01 AR specification, where we only have a protection area of plus minus 0.2 nautical miles left and right of the desired track, but this design can only be used for approach operations. With the data we analyzed, we think that it should be possible also to reduce the protection area for en route and to benefit with a little bit lower flight level than what is possible today. One of the issues, of course, what I showed you is a situation where we had a perfect GNSS performance. If GNSS is lost, we still have to do something. We did an analysis, again the same route from north to south, where we switched off GPS receiver to see what the helicopter was doing. GPS receiver has been switched off here, and the helicopter was flying with the AHARS system only. On the right, you can see again the deviation, the total system error in this case, from the designed track. And what is obvious, for the first roughly 20 miles, we were still relatively close on track, less than 0.2 nautical miles deviation, and only after significant track changes, the errors got larger and larger. But at least for some of the miles, it seems feasible to fly with the AHARS only. So that brings me to the conclusion. In this project, we recorded more than 40,000 hours of flight data, which is a statistically relevant data set and which allows several different analyses. One of them was an extended track accuracy analysis, where we reached a level of below 0.05 nautical miles, so the 95th percentile as shown is at 0.01 nautical miles. All these analyses were made with the autopilot. We also had a look at manually steered flights, where errors are usually a bit larger. Of course, GNSS outages must be managed, but the overall conclusion is that the RMP requirements are achieved with a large margin, and we think that the technology is available for more demanding operations. Thank you very much for listening.